Okay, so I want to do problem 23. Remember, the first thing that we should look at here, so the test, I'm not going to give these steps that you work through. You'll just have to know what steps to take. But the first thing that we want to look at is the phase diagram. Okay, and we only care about positive values of x. So the phase diagram is going to look something like this. This is x. This is f of x. So we're going to graph x squared times 1 minus x squared. Okay, now, using Desmos is something that is totally allowed on this exam. Okay, so definitely use Desmos if you want to, if you're not so confident with your abilities to sort of sketch what shapes of polynomials look like. But this is a fourth order polynomial, so we know the end behavior is going to be up like this. Okay, we know there's a 0 at 0 and a 0 at 1. Okay, as a fourth order, this term here is a product of squares, so we know it's always going to be positive. So we know that basically the shape is going to look something like this. Okay, another way we can tell that is that these are even roots. 0 is an even root and 1 is an even root. So it's not going to, the graph is not going to go through the x-axis, it's just going to bounce off the x-axis. So this is actually maybe a little bit inaccurate. I want to make it look like it does not go through the x-axis, so something like this. Okay, something along these lines. Okay, so remember when we're doing this stuff with increasing, decreasing, concave up, concave down, etc., the increasing, decreasing is based on the sign of f. Concavity is based on the sign of f times the sign of the derivative of f. Okay, so notice that f is always positive. Okay, so f is always positive. That means the derivative is always going to be increasing. And there is a sign change in the derivative right here when x is equal to 1/2. Okay, so here there's basically, and then another sign change here in the derivative at 1. And of course, at 0, there's also a sign change, but we don't care about x being less than 0. Okay, so we have to track through all of these different sign changes. So whenever there's a sign change of either f or f prime, that has to be the endpoint of a new interval. Okay, so first we're going to look at the interval 0 to 1/2. Okay, and on this interval, we know that f is positive, and f is still increasing, so we know f prime is positive. X double prime is just f prime times f, that's positive times positive, so that's positive, and so this is a concave up function. So solutions x that are in between 0 and 1/2 are going to be increasing and concave up. All right, now we look at the interval 1/2 to 1. On this interval, well, f is still positive. F is always positive. Okay, oh, also let me write up here, it's increasing. Okay, now in this interval, 1/2 to 1, f is positive, so okay, f is positive and decreasing, so f prime is negative. Okay, x double prime is f prime times f, so that's positive times negative, so that's going to be negative. So it tells us that these solutions are increasing and concave down. Okay, and then finally, the interval 1/2 to positive infinity, we know that f is positive there. We know that f is increasing, so f prime is positive there. X double prime is f prime times f, so that's going to be positive. So we know that this is increasing and concave up. Okay, and so now I'm going to plot a few sample solutions. And really you should plot, you're not going to have to do this on the exam because you can't graph stuff on the exam. But I'm just going to do it anyway because I think it still helps you understand stuff. So now this is not going to be the phase plane. This is going to be the graphs of the solutions themselves. Okay, so there are equilibrium solutions at x is equal to 0 and x is equal to 1. Okay, and then there is going to be a change in concavity, or like an inflection point, I guess, at 1/2. Okay, so how is this going to look? Solutions that start between 1/2 and 1. Okay, these are the green solutions. Solutions that start between 1/2 and 1. So the reason I did a dashed line at 1/2 is because that is not an equilibrium. That's just where the concavity changes. 0 and 1 are the only equilibria. So if a solution starts a little bit above 1/2, it's going to be increasing and concave down. So it's going to look something like this. Okay, if a solution starts in between 0 and 1/2, it's going to start off increasing. Well, it's always going to be increasing, but it's going to start off concave up like this, and as it passes through 1/2, it changes to being concave down. So something like this. Okay, and then finally for the red one, if it starts above 0, it's going to be increasing and concave up. Or sorry, if it starts above 1, it's going to be increasing and concave up. Okay, so for stability, let's do some stability stuff. Again, the two equilibria are x of t equals 0. This is unstable. Okay, now if you were to have dropped the x-axis below 0, you actually would see that this is semi-stable. And so if you explain it that way, you would get complete credit. But since we're only looking at positive values of x, we're going to say x is unstable, or x of t equals 0 is unstable. Because for us, negative values of x don't exist. Okay, but that's just kind of a convention. And if on an exam you were to say this is semi-stable because solutions that start below 0 go up to 0, and solutions that start above 0 go away from 0, so it's semi-stable, you'd get full credit. Okay, x of t equals 1. Okay, this is semi-stable, and again, it's semi-stable because solutions that start a little bit below 1 go up to 1, and solutions that start above 1 go away from 1. Okay, so that's it for this problem.